Alright, so let me talk a little bit about how to calculate volumes using calculus. First of all, how do you find a volume of a cone of height h and radius r? So I made a right circular cone, so it looks something, roughly speaking, like so, right? Or I guess you can draw it like this, if you like. I guess I like this one more. So this right here at the top is r. Alright, that radius is r, and this is the height of the cone, like this, alright? So what you want to do then is you want to chop this cone up into pieces of things you already know how to calculate the volume of. Now, I'm going to assume we know that the area of a circle is pi r squared, alright? Or pi s squared, as the case may be here. So let's look at a little slice. Alright, and that slice is going to have a little thickness. I guess I'll use y. Sometimes I use z there, but there's dy, and that's at position y, right? And let's say that it has radius, right? The radius, I'm going to call the radius, I'll call it s. Use s for anything else. So, okay, so the little bit of volume for this little, this little disc right here is what? What's the volume of this disc? Well, it is dV, which is pi s squared times dy. See, because the area of the cross section, the slice, is pi s squared. The thickness is dy, so this is the volume. Now the thing is, s is a function. It's a function of y. Now there's various schemes people have to figure out how s and y are related. Two major schemes. The one is right triangles, similar triangles rather. So I'll just run that by you here right quick. So we got two big triangles. Basically, I was supposed to be straight. Well, I tried. So if you look at it, there's two similar triangles. Let me do a different color. I'm an idiot. Here, there's this triangle, and then there's the bigger blue triangle. So like here's that red triangle up in here. And I won't draw well, fine, the blue one would be like all the way up here, right? Don't want to make my picture too cluttered. But the point is that this R and this H is given on the blue triangle, whereas S is here and Y is there. And so these have the same angle, right? So they share the same tangent. And so in particular, S over Y is going to be equal to R over H, and therefore S is equal to R over H times Y. The other way to do this is to notice that S has to be a linear function of Y. S of 0 is 0, and S of H has to be equal to R, so you can fit the line to do that. I'll come back to that idea again when we look at pyramids. But for now, we'll just use similar triangles. So there you go. And so then we can calculate it, right? Now this is going to be good for what? For 0, less than or equal to y, less than or equal to h, right? And so here we go. The volume is the integral of dv, which in this case is the integral from 0 to h of what? Pi s squared. So that's r over h quantity times y, that quantity squared rather, times dy. So I'm going to pull all the constants out. I've got myself a pi, I've got an r squared, and I'm dividing by, looks like an h squared. And then I have the integral from 0 to h of y squared dy. Alright, so I've got myself pi r squared divided by 3 h squared y cubed, evaluate from 0 to h. Lo and behold, that gives us an h cubed, 0 gives us 0, h cubed over h squared gives us h, and so there's the famous formula. 1/3 pi r squared h. That is the volume of a right circular cone. And there's how you derive it, slicing and dicing via the infinitesimal method and a calculus. Not too bad. What if we want to calculate the volume? So I'm just going to do 2 of these slicing examples, and then I'm going to switch over to looking at what are called solids, volumes of revolution. They're a little bit, well, no, they're more challenging or less challenging, but they're different. So suppose I have something like a pyramid, but it's not a pyramid, it's a cutoff pyramid, all right? So here's my sad attempt at a picture for it. And it has height h, in the sense that if you drew a perpendicular from the base of it up to the top, it has height h. And I'm going to assume that this has side length a and this has side length b, and it's a square pyramid, okay? So then the question then is, what's the volume, all right, for this square pyramid? So what I do, kind of same things last time, is I chop it into slices. And you might be able to do some kind of other sort of argument. I don't much care. Great if you can. But if you can't, the rest of us can do calculus. All right. So basically this slice is, I'm envisioning a distance y off the base, base of the pyramid, the thickness of it, dy, right? And I'm going to say that the side length here is L. So dV, area of the square, L squared, right, times dy. There you go. And that's going to be true for 0 less than or equal to y less than or equal to h, the height of the pyramid. Now, there's probably some similar triangle thing you could use to do it here, but I'm going to use argument by linearity. It has flat sides. So there's a specific angle that relates, you know, there's trigonometry you could do here that would relate the length of a side to the angle at the base and junk. I don't really much care. The point is that L of y, I mean I do care, but I want to do it this way. L of y is equal to my, I better not use b, the b is already used here, so let's do something else, c, all right. So there's some constant m and constant c such that I can fit the data. In other words, the data is what? L, when y equals to 0, L is given to be a. When L is equal to what? When L is equal to h, the side length of the top is given to be b. So I can figure out L as a function of y using this data. In particular, what do I got? A is equal to m times 0 plus c. So therefore that constant c is actually a. Remember, a and b are given here. The answer should be in terms of a and b. We also know that b is equal to m times h, and we just figured out that c was a plus a. So therefore, solving for m is equal to b minus a over h. There you have it. So dv, right, is equal to L squared. What is L? Well, L apparently is b minus a over h, quantity, times y, that's m, plus c, which was a. I square that, right, and I integrate with respect to y. And I have to do that again for 0 less than or equal to y less than or equal to h. Let's see here. It seems convenient then, for this kind of problem, v is equal to, of course, this integral, right? I mean, you could just FOIL it out and do the calculus, but I kind of like to do u substitution here. I'm going to let u equal to b minus a over h, all right, times y plus a, all right? And if I do that, that makes du equal to b minus a over h times dy, right? In other words, dy is equal to h over b minus a du. And what else here? Well, let's see here. U of 0 is what? U of 0 is A. U of H is what? It's B, isn't it? Of course, that's not surprising. U is exactly L. So anyway, I'm just saying rewrite the integral in terms of L, it's easier. So we have integral from, I mean, fine, I guess if you're a little bit more bold and geometric, you could just say, it's the integral from a to b of L squared times, well, the thing is you need to see that instead of putting dy, yeah, I mean, there's, well, you'll see in a second here. This maybe is not intuitively obvious. Maybe, I don't know, maybe it is. Anyway, a to b of u squared, and again, this is h over b minus a times du. And so I'm going to move it over here so I have more room. So this gives me 1/3 times h over b minus a, right? Then u cubed. Well, I mean this, and then I've got u cubed evaluated from a to b. I pulled the 1/3 of the antiderivative out front, right? All right, so that's 1/3 h over b minus a times b cubed minus a cubed. This can be simplified because b cubed minus a cubed is what? You guys remember? So b cubed minus a cubed is b minus a times what? Times b squared. I think it's b squared plus ab plus a squared. We can check if that works, right? B times, that gives me my b cubed. I've got my minus a cubed. Does everything else cancel? Minus ab squared plus ab squared and plus a squared b minus a squared b. Yeah, that's it. So this is equal to the b minus a's cancel, and you're left with 1/3 h times a squared plus ab plus b squared, which is kind of cool. So there you go. That is the volume of such a pyramid. The main point, of course, being here that you know this idea of chopping a solid with some sort of regular cross-section up into pieces, and then you can do an integral according to the area of the cross-sectional slice. This, of course, presupposes a certain regularity of the area of the volume. You have to have the situation that you can somehow parameterize or describe, if you like, the area of the cross-section in terms of the coordinate along the axis, which is perpendicular to the cross-section, right? I mean, you need that situation. If you don't have that situation, you can't do the integral. And then you need calculus 3 to do more complicated volumes of uglier things. But anyway, all right, I'm going to start again with solids of revolution. Thanks, guys.